All right, in this video, we're going to talk about suggested homework problems from 3.7. This covers optimization. It's going to feel a little bit like related rates, in that we're going to have to know a lot of geometry problems or geometry formulas and things like that. Key idea here is that we're usually going to have two equations that we're dealing with: a constraint equation, which is equal to a constant of some kind, and an objective equation, which we want to minimize or maximize. Watch for the words minimize and maximize, and that will tell you what your objective function is. We'll have to use our constraint function to eliminate a variable in our objective function, and then differentiate our objective function, set it equal to 0, and use our first or second derivative test for extrema to prove that we have the minimum or maximum that we are looking for at the critical numbers that we have found. And you'll see that as we go along here. So let's start with number 5. They do not give us a number here for our constraint equation, but just treat capital S like it is a constant in this one, even though we don't know what it is. So we have capital S is equal to x plus y. And we have our objective function as area, which will be x times y. Solve for x or y. I'm going to solve for y. Will be capital S minus x. So a of x will turn into x times s minus x, or a of x will be sx minus x squared. So I want to differentiate a now, which is my objective function, s minus 2x, and I want to set that equal to 0. That gives me 2x is equal to s, and x is equal to s over 2. Now, because I don't have a number for s here, I really don't want to try to do the first derivative test if I don't have to. Let me try the second derivative test here. Second derivative is going to be a -2, and if I plug s over 2 in for x, I'm still going to get a -2. So there's a local min at x equals s over, a local max. When the second derivative is negative or concave down, and there's a local maximum at x equals s over 2, y equals s minus s over 2. It's also s over 2, so my two numbers are s over 2, s over 2. That was number 5. We'll look now at number 7. Our constraint equation this time is the product of the two numbers, which will multiply to give us 147. So xy equals 147 is my constraint equation. And we're going to add in kind of a funny way. We're going to take the first number plus 3 times the second number, and we want that to be a minimum. Minimize s here. So I'll solve for x here to get everything in terms of y, 47y to the negative first. So s of y is 147y to the negative first plus 3y. S prime of y is a negative 147y to the negative second plus 3. And I'll turn that into 3y squared minus 147 over y squared. I didn't mention this in the first problem, but x and y, we were told in our instructions, have to be positive numbers here. So I'm ignoring 0 as an option, and I'm ignoring any negative answer. S prime of y is equal to 3 times y squared minus 49. Y squared, that's 3 times y plus 7 times y minus 7 over y squared. So the only interesting answer to me is y equals 7. Using my first derivative test here, starting at 0, let's put 1 in, positive, positive, negative over positive, that's negative and decreasing. And then number bigger than 7, positive, 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 positive is positive and increasing. So there's a local min at y equals to 7. And that makes x equal to 147 over 7 is 21. So my numbers are 21 and 7 for my xy ordered pair, where my minimum sum occurs and the product is 147. Moving on now to number 15. Y equals x squared 0.03. We have our distance formula. I'm going to call it r. It's equal to the square root of delta x squared plus delta y squared. We'll be using that in just a minute. And I'm going to square both sides to basically get the Pythagorean theorem here. Because if r is going to be a minimum, r squared will also be a minimum. So I might as well just use the formula for r squared. And I'm going to turn this into some function of x or y, and I'll probably call that g of x or f of x or something like that, since this is called y. So, all right, so r squared is going to be x minus 0 squared plus y minus 3 squared. R squared is going to be x squared plus, and then y is the same thing as x squared minus 3 quantity squared. And I'll replace r squared with f of x here. So f prime of x is 2x plus 2x squared minus 3 times 2x. I set that equal to 0. I'm going to factor out a 2x, and that's 1 plus 2 times x squared minus 3. It's equal to 0. And then 2x times 1 plus 2x squared minus 6 equal to 0. 2 times 2x squared minus 5 is equal to 0. 2x equals 0, or 2x squared minus 5 equals 0. 2x squared equals to 5. X squared is equal to 5 halves. X is equal to, again, plus or minus the square root here. X does not have to be a positive number in this case. We have all real numbers that we're allowed to deal with. So be careful there. That's not like the previous problems. Let's set up our number line here. For our first derivative test, we have 0 in the middle. We have negative root 5 over 2. We have positive root 5 over 2. Let's check and see what the value of that is so that we have an idea what numbers to choose for test points. So I'm good if I choose -2 for my x value here. Negative, and then positive will be negative and decreasing. A number like -1 will be sufficient here to give me negative, and negative is positive and increasing. 1 is positive and negative, which is negative and decreasing. And 2 is positive and positive, that's positive and increasing. So I'm interested in the local minimum here for the distance, which is going to be at x is negative root 5 over 2 something, and root 5 over 2 something. And let's come back to the y is x squared. So when I square this, this is 5 halves. When I square this, this is 5 halves. And those are my xy ordered pairs. I don't need to do anything else. It doesn't ask me to find what the minimum distance is. So I'll just leave it at that. Move on now to number 17. We have a poster with some print area. We have margins on the left and right of 1 inch. And on the top and bottom of 2 inches. This is X. This is Y, which makes this X plus 2, and this Y plus 4. This printed area needs to be 648 square inches. So XY equals 648. And then we want to minimize X plus 2, let's call it area A equals X plus 2 times Y plus 4. So to do that, I'm going to make a substitution for Y. Y equals 648 over X. A of X is X plus 2 times 648 over X plus 4. So that's 648 plus 4X plus 1296 over X plus 8 is 656 plus 4X plus 1296 X to the negative first. So this is 4 minus 1296 X to the negative second. So I'll turn that into 4X squared minus 1296 over X squared and factor 324 square root of 324. It's going to be 18. So that's 4 times X plus 18, X minus 18 over X squared. Context of the problem demands that X and Y be positive numbers here. So X is going to be a positive 18. And if X is 18, then we can use a number a little bit less than 18 to say positive, positive, negative, or positive is negative and decreasing. Number a little bit bigger than 18, positive, 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 positive is increasing. So there's a local min at X is equal to 18. If X is 18, Y is equal to, and these are inches, is equal to 648 over 16. Over 18, sorry, for 18, 648 over 18 is 36 inches. Now be careful because that gives me my print area. So that gives me that this is 18 by 36, but I wasn't asked that. I was asked about the total dimensions of the poster board. So 18 plus 2 is 20 inches and 36 plus 4 is 40 inches. So my dimensions of my poster board are going to be 20 inches by 40 inches. Final answer. Let's look at number 19 now. We have a picture to go with this one. So we have Y and X. And then on this side is a river. So that you know what that blue stuff is in the picture. That's a natural boundary, that's a river, that we don't need to put any fencing on that side because whatever animals we're going to put in this pasture don't like water and they're not going to try and cross the river. They're probably sheep, because sheep don't like moving water. So area of the pasture is 405,000 square meters. And perimeter here is x plus 2y. This area is x times y. So x is equal to 405,000 divided by y, and p of y is 405,000 divided by y plus 2y. So I'm going to call that 405,000 y to the negative first plus 2y. When I differentiate that, I get negative 405,000 y to the negative second plus 2, which will turn into 2y squared minus 405,000 over y squared. And then p prime y is 2 times y squared minus 202,500 over y squared. Set that equal to 0. Plus minus 450. Again, these need to be positive distances here. So the only answer that makes sense is y is 450 meters. If y is 450 meters, then x is going to be 405,000 divided by 450. Is 900. So my dimensions are x is 900 meters by y is 450 meters for my pasture. Let's look now at number 21. This Norman window problem kind of fools you with the picture. We're not really interested in talking about framing. That is this blue part that I'm coloring in right there. We're only talking about the outside part for the framing of the Norman window. So we're looking at that semicircular part right there, and this rectangular part right here without the crossbeam that would cut the circle in half or finish the rectangle. So we only have one of the X pieces. Down here, we have two of the Y pieces. We need to consider that the radius of this semicircular piece is X over 2. It's half of the distance here. And so we would have the perimeter, we want to call it that, of this is half of the perimeter of the circle, whose radius is X over 2. So perimeter or circumference of the circle is 2 pi r, and then plus, and then this perimeter is X plus 2y, and that needs to be equal to 16 feet. So half and 2 cancel each other out. P is pi over 2x plus another x plus 2y, and that equals 216. Our objective function is area. Area of the semicircle is half of pi r squared. And then area of the rectangle is xy. So we have pi over 2 times x squared over 4 plus xy. So area is pi over 8 x squared plus xy. Let's go ahead and solve for y in this constraint equation here. That 2y is equal to 16 minus pi over 2x minus x. And y is going to be 8 minus pi over 4x minus 1/2 x. So a of x is pi over 8x squared plus x times 8 minus pi over 4x minus 1/2 x. Let's distribute. A of x is pi over 8x squared plus 8x minus pi over 4x squared minus 1/2 x squared. And then when I take the derivative of this, a prime of x is pi over 4x plus 8 minus pi over 2x minus x. And I want to set that equal to 0 and solve. So let's take my x's over to the other side of the equation, since most of them are negative, and leave the 8 to be positive. I have x plus pi over 2x minus pi over 4x is equal to 8. So pi over 2 minus pi over 4 is pi over 4. And so if I pull an x out, I have 1 plus pi over 4 x equals 8. And so I have x is equal to 8 over 1 plus pi over 4. I want to eliminate that complex fraction there. I'm going to call this 32 over 4 plus pi, or pi plus 4. And that is going to be my x value. I'm not going to try to do a first derivative test on that. I'll do a second derivative test here. That second derivative here is going to be pi over 4 minus pi over 2 minus 1 is a negative. Pi over 4 minus 1 is less than 0, so there's a local max at x equals 32 over pi plus 4. And if I have x equals that, then y equals to 8. Let's see, copy this. 8 minus pi over 4 x minus 1/2 x, like that. So y equals 8 times pi plus 4 over pi plus 4 to make a common denominator, minus 8 pi over pi plus 4 minus 16 over pi plus 4. Y will be 8 pi plus 32 minus 8 pi minus 16 over pi plus 4. So 16 over pi plus 4 is my y value, giving me 32 over pi plus 4 for x and 16 over pi plus 4 for y for my dimensions. Let's move on now to number 25. '25 says y equals root 25 minus x squared, and they give us a picture here of that this is the top half of a semicircle, or top half of a circle. They give us that we have our x-axis and y-axis coming through the center of the circle, and we want to inscribe a rectangle here where this point out here is x, y. And so x and y are both going to be positive numbers since we're in quadrant 1. It's going to be important later. And we want to maximize the area of the rectangle. So pay attention to the fact that this is x and this is y, but the entire rectangle has a length of 2x and a width of y, so its area is 2xy. So area is 2x root 25 minus x squared. I'm going to tell you again, we've done the same type of thing, that if a gets minimized, a squared will also get minimized. I don't want to deal with that square root in this problem. I'm going to minimize a squared instead. So that's 4y squared, 4x squared times 25 minus x squared. And I'll call this f of x for you. So f of x is equal to 100x squared minus 4x to the fourth. F prime of x is equal to 200x minus 16x to the third. And both of these are divisible by 8. I'm going to pull a negative 8 out is 2x and an x out. 2x squared minus 200 divided by 8 is 25. Set that equal to 0. X equals 0, or x equals plus or minus root 25 over 2. And x has to be a positive number. We just said that. So x has to be 5 over root 2, which is 5 root 2 over 2. Let's use my second derivative test here to prove that this is a maximum. So this is 200 minus 48x squared. It's 200 minus 48 times 5 over root 2 squared. It's 200 minus 48 times 25 over 2. 2 goes into here 24 times. And 4 times 25 is 100, leaving 6 there. So this is 200 minus 600 is a negative 400. So we have a local max at x equals 5 root 2 over 2. And then my y value was, what's my y value? 25 minus y is root 25 minus x squared. So y is root 25 minus, and then 5 over root 2 squared is root 25 minus 25 over 2 is root 25 over 2 is 5 over root 2 is 5 root 2 over 2. So x is 5 root 2 over 2, y is 5 root 2 over 2, but those are not the dimensions of my rectangle. Remember, my length needs to be 2 times x. So this is going to be 5 root 2, and this is just, I'll say units because they didn't tell me what my units were here, by 5 root 2 over 2 units will give me the maximum area. All right. Let's go ahead and look at number 29. And we need to add the length and the girth here, where we have a square base, I'll call it here. So we have y plus 4x is going to give me 108 is what we're given as our, and these are inches. That's our constraint equation. And we want to find volume of this. So volume of this shape here is x squared y. Let's solve for y. Y is 108 minus 4x. So volume with respect to x is x squared times 108 minus 4x. It's 108 x squared minus 4x cubed. V prime of x is 216x minus 12x squared, set equal to 0. And then I'm going to factor out a negative 12x, x minus 18, 216 divided by negative 12, the negative 18. And then x has to be greater than 0 and y have to be greater than 0 in this situation here. So x equals 0 doesn't make any sense. X equals 18. Let's test this. 0, 18 on 1 here. Negative times a negative is a positive and increasing. Negative and positive is negative and decreasing. There's a local max at x equals to 18. Y is equal to 108 minus 4 times 18. 108 minus 4 times 18 is 36. These are inches. So our dimensions are 36 inches in length by 18 inches in width by 18 inches in height. Moving on now to number 33. They're not calling this a capsule, but this is a capsule is what they're talking about here. That we have a hemisphere, a right circular cylinder, another hemisphere to make a capsule. If we put the two hemispheres together, then their volume would be the volume of a sphere, 4/3 pi r cubed, and the volume of the right circular cylinder is pi r squared h. And altogether, that total value needs to be 14 cubic centimeters. Our surface area, which I'll call capital S, is going to be, you may not know this one, but it's 4 pi r squared for a sphere, and it's 2 pi r h for a cylinder. And we want to minimize that surface area because that will minimize the cost of producing this. H is the oddball out here, so I'm going to say that 14 minus 4/3 pi r cubed is equal to pi r squared h, and then divide everything by pi r squared to get h by itself. 14 over pi r squared minus 4/3. Pi will cancel, I'll be left with r. And then h goes in place of h in the formula here, 4 pi r squared plus 2 pi r times 14 over pi r squared minus 4/3 r. S is 4 pi r squared plus, this is 28 pi r over pi r squared minus 8 pi r squared over 3. So we'll reduce here, and I get S is 4 pi r squared plus 28 r to the negative first minus 8/3 pi r squared. So S prime is 8 pi r minus 28 r to the negative second minus 16/3 pi r. And let's do this. 24 pi r over 3, 16 pi r over 3, 28 r to the negative second. Put those like terms together is 8/3 pi r minus 28 over r squared. Need to multiply by 3 over 3 here and by r squared over r squared here to make S prime equal to 8 pi r cubed minus, let's see, 28 times 3 is 84 over 3 r squared. And then I have a 4 that can come out, 2 pi r cubed minus 21 over 3 r squared. So r needs to be positive. H also needs to be positive, or could be 0 in this case, but r definitely needs to be positive here. So 2 pi r cubed minus 21 needs to be 0. 2 pi r cubed equals 21. R cubed equals 21 over 2 pi, and r is the cube root of 21 over 2 pi. Now, that's all that they asked for was that value. I know that that's the right value. It didn't ask us anything about h. I'll tell you that if you go and do the work to solve for h, you'll find that h of r being cube root of 21 over 2 pi is 0, meaning that you just have a sphere, you don't have a capsule. That's how you're going to minimize your surface area and get your volume that you want, is to put all the volume inside of the sphere and to get rid of the cylinder piece that's in between. So this will happen when r is equal to cube root of 21 over 2 pi and h is equal to 0. That's when my minimum surface area is going to happen. Let's look at 43. If f of x is equal to 2 minus 2 sine of x, then, and we're on the interval from 0 to pi over 2 with those points included, let's find our y-intercept. F of 0 is 2 minus 2 sine of 0. is 2 minus 2 times 0 is 2 minus 0 is 2, giving me a 0.02 for a y-intercept. My x-intercept will be when 2 minus 2 sine x is equal to 0, negative 2 sine x is equal to a negative 2, sine x will be equal to 1, and in this interval that only happens at pi over 2, giving me pi over 2, 0 as my x-intercept. So x-intercept, y-intercept. All right, so distance from 0, 0 to y-intercept is 2. Distance from 0, 0 to x-intercept is pi over 2. Generic distance formula, they tell me to use d. I'm not going to use d. I'm going to use r. Because we are centered at 0, 0, that's where we want to find the distance from. Then r is going to be the square root of x squared plus y squared, will be the square root of x squared plus 2 minus 2 sine x quantity squared. If I had been finding the distance to any other point other than 0, 0, I'd have to do delta x squared and delta y squared and take into account the x and y values of that point. All right. Use calculus to find the value x that minimizes the function. Okay, so we're going to square both sides. If r is a minimum, r squared will be a minimum. I've done this quite a bit in this section. I think that you should be okay with that idea now. But sometimes we want to get rid of the square root because they're nasty to take derivatives of. So call that g of x. G prime of x is equal to 2x plus 2 times 2 minus 2 sine of x times a negative 2 cosine of x. We're going to have to use our calculator here because we have no way to solve this equation here without it. So let me simplify this just a bit though. Minus 4 cosine of x times 2 minus 2 sine of x is 2x minus 8 cosine of x times 1 minus sine x. All right, so that's easy enough to type into the calculator. Y equals 2x minus 8 cosine of x times 1 minus sine of x, close parentheses for sine, close parentheses for the grouping symbol, and I will zoom trig, and I'm interested in the x-intercept here, second calc 2. And x is approximately 0.796723. We're not going to talk about it in our suggested homework problems, but the next section of the book talks about Newton's method and would help you to be able to find that x-intercept to a certain number of decimal places without the calculator. So we have no way to do it in this section of the textbook without the calculator. The technique to use is actually in the next section of the textbook. Look at that if you want to, but it's kind of going to be covered in differential equations. So we will not be doing any suggested homework problems for that. We want to come back and talk about f of 0.796 7243. We can go back and do that with two minus 2 sine of the x value that we just found, and that's going to be 0.569859897. And if I take and want to find the distance from, let's see, so here's the ordered pair 7967243 to 0.5698598947. So take x, so hang on, square root of x is still in there, x squared plus answer that I just got squared will be my x squared plus y squared, and my distance r is 0.979545777. So I'm going to approximate everything to 4 decimal places just because I feel like the calculator is good up to 4 decimal places. So I'm going to cut this off here and make this here and this 2, 3, 4 right there. That's pretty good, and that's what I'm going to go with for my answer for what the minimum distance is. That's right there. And let's I don't think there's a way to do this on the graphing calculator to get distance from, no, there's no way to get distance on the calculator. So that's it. I think that that's all we can do is plug the values into the graphing calculator to get the answer, and that's what it's going to be. All right. That's it for this video. Like I said, we're going to skip 3.8 because it's covered in differential equations. We don't really use it in calculus anymore because we have technology that is better than Newton's method. We just use our TIA 83 or 84 calculators to find zeros of functions when we can't find them by hand, and it does a really good job. And so Newton's method is the old method prior to calculators. It's long and tedious and only gets you a certain level of precision. Calculators way better, much more efficient, and it's really not worth teaching you Newton's method right now unless your teacher tells you to do it. If you have questions about Newton's method because your teacher wants you to do any problems in there just as a not as a main objective for the course, but as something extra that your teacher wants you to do just so you're exposed to it, you can let me know. Come see your tutors in your tutoring center at your school. See if they can go over those problems with you just for that section. But there you go. This is 3.7. We'll come back next time and talk about 3.9. See you for the next video.